So let us continue with our discussion. Okay, we are talking about resistive temperature detectors. Okay, so what I was mentioning here is, so we have taken a copper wire which is of length 1 meters, and the area of cross section is 0.1 mm square. So we have now taken that resistors, that's the conductor, which is now having a resistance given by the expression whatever you see here. So we have taken that and we have included into a circuit. So there are two resistors that are connected in series, and there is a voltage applied across these two resistors. We are tapping the voltage across the sensor now, or a transducer. Okay. Let me take the whiteboard and illustrate how does this work. So we are now having two resistors. There are two resistors, and across which we are applying a voltage. So this is your voltage V in. Okay, it's a DC voltage. This resistor is R1, and this is your transducer which is used to measure temperature. So we know that since the resistance are now connected in series, okay, the voltage across this resistor, okay, is V in. Now let us take the voltage across resistor RT. So now we denote it as VT. So whenever the room temperature T, if it is 27 degrees centigrade, okay, centigrade, so the resistance RT would be some value. If the temperature changes, here, the resistance also changes. Because the resistance is going to change, VT is also going to change. So if you see here, the resistance VT, which is now a measure of temperature. So VT is now directly proportional to what? Temperature change. But how is the VT is going to change now? VT is going to change because whenever the temperature changes, this temperature changes resistance, and resistance is now going to change what? VT, that is voltage. So this is now called as a secondary transducer because the voltage is now not directly related to temperature, it is related to resistance, and resistance is related to what? Temperature. Okay, now let us see what would be the temperature across this device. So you have a resistor here, and we are applying voltage equal to now VT. This is voltage which is equal to VT. We are measuring voltage here which is VT, sorry, this voltage is now V in. The voltage what we are applying is V in. We are now trying to measure the voltage across the transducer which is RT in terms of VT. Now what will be the resistor now? Voltage now. The voltage is now given by a very important formula given as voltage divider theorem. As we apply voltage across these 2 points, the voltage will now get divided into two voltages. One will be across this, we call it as V1, the other voltage is now equal to VT. Now using this voltage divider theorem, okay, we find that the voltage across this RT is now going to be V in, the main voltage, into RT, that is the resistance here, divided by RT plus R1. So the voltage that is going to be available here across the transducer RT is based upon voltage divider theorem, which states that, okay, the voltage VT is now equal to V in, the main voltage, into resistance RT divided by RT plus R1. Here R1 is fixed, V in is fixed, RT is going to change. As RT is going to change, voltage is also going to change. So this is how we measure the voltage change related to temperature change. So this is also called as your voltage dependent resistor, or it's a temperature dependent resistor, or it is basically, okay, your voltage divider network which is able to change its voltage for changes in temperature. Okay. Yes. Instead of using a series network, what we can also do is, see, we can also use a bridge network. I can use a Wheatstone's bridge like this. there are 4 resistors connected into a bridge. What we can now do is, we can apply a voltage across this bridge. So we can apply a voltage called V in, and further measure the voltage across these 2 terminals. Now we can take it as R1, R2, R3, R4. When the bridge is balanced, okay, what do you mean by bridge is balanced? R1 by R2, if it is equal to R3 by R4, the voltage that is available here, VT voltage, VT, if it will be equal to 0. Now let us assume that this R4 is a transducer, and this is now going to change its value. The resistance of R4 is now dependent upon temperature, that is R4 is now proportional to temperature, because it is a transducer now. As the temperature changes, R4 also changes, and because R4 is going to change, the bridge becomes unbalanced. So what will happen? VT is also going to change. Instead of 0, it may show you some positive value. So we can even use a resistor into a bridge network, and we can measure the amount of voltage that is going to be available across the bridge, and that voltage is directly proportional to change in temperature. Yes. So the change in temperature is now related to resistance. So either I can use it into a series network, or I can use it into a bridge network to convert the change in resistance to voltage, and that is what we call it as resistive temperature detectors. Let us go to the types of RTDs. So the RTDs can be glass encapsulated RTDs, thin film RTDs. So what you see here, the first picture is basically a glass encapsulated RTD. So what we do is, we take a thin wire, we take it into a thin wire and encapsulate into a glass cylinder. So what happens whenever there is a change in temperature? So we dip it into hot water, or we dip it into hot chemical, or we dip it into a hot device. As soon as we place it on a hot device, the change in temperature is now going to change the resistance of the wire available within the glass tube, and that change can be detected using your series network, or it could be used using in a bridge network to change the resistance. It could also be a thin film. So this is a thin film circuit what you come across, a thin film. So what happens, as the temperature changes, the resistance of the thin film also changes. So you are able to find out there is a linear relationship between temperature and resistance. So that is what we call it as resistive temperature detectors. Yes. Yes. Now let us also understand the other kind of RTD, it is called as thermal resistors. It became available in 1960s, and this thermal resistor can be NTC. It could be it is negative temperature coefficient, it offers high resistance, and it is having high temperature coefficients. Let us just watch a small video on what is this thermal resistors, and then understand the discussion on thermal resistors.
Hi folks, I'm going to talk about a little electrical component for measuring actually needed water temperature experiments.
Close ಮಾಡಲಾ? Okay, so there is a technical issue with respect to playing the video. So let us understand what is this thermal resistor or thermistor is. Okay, this thermistor. Okay, let us just close ಮಾಡಲ್ಲ ಇದರಿಂದ ಓಪನ್ ಮಾಡಲ್ಲ ನೋ ಆಗಲ್ಲ. Okay, so there is a small technical problem because the video that I have taken doesn't support the resolution here, and now it has introduced some amount of virus, so we are unable to play the video. But this video is actually available on YouTube. You can download this video, plus it is also available on our VTU website. Okay, you can use that video. Also you can visit our MSCC website to know more about this video. Right? This video was supposed to just illustrate what is a thermal resistor is, or simply called as thermistor. What this video can do, okay? What is that which is being shown in the video? So what happens in this video is a small thermistor is taken. Okay, this thermistor is able to measure the amount of change in temperature in terms of current. Okay, and it is used in an automotive. And what is also been done is in this simple video, YouTube video, they are able to design this thermistor. Okay, and then they are able to take it. And it is able to take it, and then we are able to put it into a hot water, and then when the hot water starts boiling, the temperature keeps changing, and we have taken a small circuit, okay, and that circuit is connected to a voltmeter to understand how much of change in voltage occurs because of change in temperature. Okay, so we will not run this video. So let us continue with our discussion, right? Okay. So in a thermistor, what happens basically is, okay, it is governed by a simple expression wherein the resistance of a thermistor is now given by an equation R of T. Okay, it's now temperature dependent resistor, which is equal to alpha in times into E beta by T, where alpha and beta are the constants, and R of T is the resistance of the device, and T is the temperature of the device. Okay, the relation is non-linear, but only mildly non-linear because beta is going to be very, very small. Okay, and approximately, okay, it is like just a transfer function. Let us now see what is this devices. Okay, so the construction of these devices. So what we do is, it can be like a bead, it could be like a chip, it could be deposited on a substrate. So this is how a bead is. Okay, so what we do here is, okay, we have a oxide here, okay, and it is encapsulated. Okay, it could be oxide here, and then it is like a small device. It's like a small bead, wherein we have a small device inside it, which is now working as a thermistor. Yeah. Now this thermoelectric effect is based upon Seebeck effect, which was identified in 1821. Okay, it's a very long time they could identify the sensor, and it was identified in 1821. Okay, now this Seebeck effect is the sum of two other effects called the Peltier effect and Thomson effect. So if at all you would like to remember, okay, what is thermoelectric logic? Thermoelectric logic is based upon Seebeck effect, and the Seebeck effect is a combination of two more effects called as Peltier and Thomson. Okay, now let us see what is that Seebeck effect is. The Seebeck effect is an EMF produced across the junctions of two dissimilar conducting materials connected together. So what we do is, we take two materials like A and B. A and B are two conductors which are of two different materials. Okay, now we connect them at two different points like T1 and T2. Okay, if both ends of the two conductors are connected and the temperature difference is maintained between the two junctions, a thermoelectric effect or thermoelectric current will flow through the closed circuit. So what is happening here? The Seebeck effect states that if I take two conductors, okay, of two different materials, and I connect them at two different junctions, now what I do, I try to take the two different nodes, at two different temperatures. This temperature may be at 27 degrees centigrade, this temperature may be at 30 degrees centigrade. Because of change in temperature, what basically happens is there is a current flowing in this conductor. So to lead to Seebeck effect, what is required now? I need to have two different materials, and they are connected at two different nodes, and I am able to place them at two different temperatures. Because of the change in temperature, what happens? A current starts flowing in the entire loop, because there is a closed loop circuit now, and that effect is now called as Seebeck effect, right? Okay. Now, because of these two nodes at two different temperatures, okay, if at all I open at one part of it and I make it as an open circuit, an EMF is going to get generated, and that EMF can be measured. Now, this EMF that we are able to get at this point is a measure of the temperatures that are available across these two nodes. And now, if the circuit is opened, an EMF will appear across the open circuit. It is this EMF that is measured in a thermocouple sensor. So we are now talking about a concept called thermocouple. What happens in thermocouple is we now have two conductors. Okay, these two conductors are of two different materials. We tie them at two different nodes, T1 and T2, and if I take T1 and T2 as two different temperatures, what happens? If I open it up, there will be a small amount of EMF generated, and that EMF will be now dependent upon the temperature available at two extremes of these nodes, and that is what is called as Seebeck effect. Okay. Now let us see what can a thermocouple do. So what we do here is there are conductors A and B which are homogeneous, and there are two junctions T2 and T1. On junction T1, okay, on junction 1 and junction 2, the total EMF is, for example, if I take EMF A, okay, it is alpha A into T2 minus T1, and EMF B, that is the EMF available across this, is going to be EMF B is equal to alpha B into T2 minus T1. And if I try to take the EMF at this point, it will be EMF A minus EMF B, which is equal to be alpha A minus alpha B into T2 minus T1, which is going to be alpha times AB, alpha AB into T2 minus T1. So this is the amount of EMF that is basically being observed at this point because of change in temperature, and that is what is the basic principle of a thermocouple. Okay. Now, how do we use these thermocouples? Okay, these thermocouples can be used, okay, in a similar way, which is shown in this picture. We can use one junction for sensing, one junction for reference. Reference temperature can be lower or higher than sensing temperature. So what we now do here is, okay, so we now have a thermocouple that is consisting of B a material, A another material, A is another material, B is another material. Okay, there are multiple nodes now. Okay, you have nodes like, okay, nodes like T1, you have nodes like T2, okay, you have nodes like T3 and T4. So T1, T2, T3, T4. There are four different nodes. Okay. Now what we do is T4 is a node, okay, it is a temperature node which is basically formed because of 6 and 5. T3 is because of 3 and 4, and T2 is because of T2. Okay, that is the node 2 is because of T2, and we have one more node here, that is T1. So what we do is, okay, junctions 3 and 4 are identical. That is, these two are identical here. These two are identical. One between material B and C, and one between material C and B, and their temperatures is the same. So now net EMF due to this pair. So what happens? Okay, because they are at same temperature, there will be no any change in EMF. Okay, junctions 5 and 6 are also produce zero field. So these two produce zero field because they are again at the same temperatures. So what we do, we can either use T2 or T1 as, okay, we can use T1 as reference and T2 as the measurement node. So what we do here is, okay, so we are now trying to make T3, okay, T4 common nodes. The temperatures there are remaining common, so there will be no change in EMF, but the node here, that is T1 and T2, are used for measuring the change in temperature. So what we now do is, okay, we can place T1 in a ice cube, okay, then we can place T2 to a physical quantity where temperature changes have to be measured. So whenever we try to make the temperature measurement with regard to T1, so we now use T1 as reference and T2 is now the node for sensing. So what happens with regard to this T1 or with regard to this T2, what happens? A small change in EMF occurs at this point, and that is what is going to be measured, and that is what is the basic function of a thermocouple, right? Let us go forward. Yes. So let us summarize. So we understood, okay, RTD, and RTD is, okay, yeah, clear madboda? Okay. So now let us play the video. Let us go back. Okay, okay. Back ಹೋಗಿ play ಮಾಡಬೇಕು. ಇದಲ್ಲ ಹಿಂದೆ ಒಂದು ವಿಡಿಯೋ ಇತ್ತಲ್ಲ, ಬೇಡ. Okay, now let us summarize. The summary is this. So we discussed about resistance temperature detectors. In a resistance temperature detector, what happened was, we have taken a small wire. Okay, this wire, we know that the length of the wire is fixed, the cross section of the wire is fixed. So we have taken a wire, the cross section, length of the wire, both of them are fixed. But we all know that the resistance of the wire changes with regard to temperature. Because the resistance of the wire changes with regard to temperature, we can use this as a transducer. Martira? Okay. Let us play the video and try whether we can have a look at the video, which will help us in understanding the sensor. Yeah, good. We are able to solve the technical problem now. Yes. See, what is being done in this video is, okay, we have taken a temperature sensor, and it is now we are able to control. We have a thermistor there, a thermal resistor, which is like a bead. Okay, this is thermal resistor. So wherein the temperature, as the temperature changes, resistance also change. We call it as positive temperature coefficient. When the temperature increases, if the resistance reduces, it is negative temperature coefficient. Yeah. That is the thermistor there, which is being packed. Yeah, inside that, we are able to place the thermistor as a bead. ಆಡಿಯೋ ಬರ್ತದೆಯಾ?
I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with the thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. Now I use this hairdryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching. See my YouTube channel, rimstar.org, for more videos like this. That includes the video containing the experience.
So that's a very nice video to really understand what is a thermistor is. Okay. So in that, if you could see, it was like a bolt, a nut, and all. So wherein it was inside, there was a bead which was placed, and that bead, two terminals, one of them was connected to the surface, the other one was connected to the screw. So we use it to measure the temperature, and it is used in automotive applications. Okay. So that is how the simple video could illustrate us how a temperature sensor, a thermistor or a temperature sensor, could be used to do some small control of fan. So as the temperature increases, okay, at normal temperature the resistance was very high, so the fan couldn't run because there was current less. As temperature increased, the resistance reduced, more current was able to flow, and fan was able to move, and that is how you can cool the room. Okay, the temperature is reduced. That's what is a simple video illustrating the usefulness of a temperature resistor or thermistor. Now let us go to next very interesting transducer called as linear variable differential transformer. Okay, it's a very synonymous name. Most of the applications, like in automotive, they use this LVDT. So we call it as LVDT because it is used as linear variable differential transformer. So what we find here, we have a transformer, then this transformer is going to it's going to have a linear variation, but it is going to be a differential transformer. Let us understand what will be the applications of linear variable differential transformer. Okay, yes. Let us understand the basics. The basics are, okay, inductance. Inductance is given by a formula L is equal to phi by I, where phi represents the flux, okay, or the it is given by Weber by ampere or Henry, okay, and the current that is flowing through the coil. Okay, it's a ratio of flux and the current that is produced. Inductance is independent of current since phi is current dependent. All magnetic devices have an inductance, but inductance is most often associated with coil. So what we can do is, if I take a coil and if I take a wire and make it as a coil, okay, if I make it as a coil, and if I pass a current through the coil, the current will now start flowing through the coil. Because it is an alternating current, there will be a flux generated, and that is what the inductance, okay, the inductance of the coil, okay, it depends upon the phi and I. Now let us see. There are two types of inductance called as self-inductance and mutual inductance. Self-inductance is the ratio of flux produced by a circuit in itself and the current that produces it. So what happens in a coil like this, if you take a voltage and you are able to make a current to flow through the coil, what happens? There will be an inductance. This inductance will further give you another inductance, and that is what we call as self-inductance. Okay. Now, what happens in mutual inductance? You have a coil, plus we have another coil which is just wound, and there is no voltage applied across this coil. The voltage, whatever we apply to this coil, okay, the current starts flowing in the coil, and the current starts moving in the coil, and because of that, a flux is generated. Now this flux, what it does is, this flux influences the coil next to it, and further there is a voltage generated, or there is a current flowing in the coil, in the secondary coil. So this we call it as primary coil, and this we call it as secondary coil. So mutual inductance is the ratio of the flux produced by the circuit current I in circuit J and the current in circuit I that produced it. Okay, so it is denoted by M of Ij. Okay, yes, and that is the basic principle of a transformer. Okay, what happens in a transformer now? There are two coils, the primary coil and the secondary coil, and then we have a core. These are the core. So what happens whenever a voltage is applied, there is a current flowing through the coil, okay, and then because there is a core available, you come across phi 1. This phi 1 influences phi 2. Further, there is a current flowing through phi, your secondary coil, and there is a voltage available across this. Now, the voltage what you can come across in the secondary coil is given by V2 is equal to N2 by N1 into V1. So now what happens? Let us understand this. Okay. So what is happening here? We now have a coil which is called as primary coil, then we have a secondary coil. So whenever we apply voltage across the primary coil, the current starts flowing in the primary coil, then it creates a flux. This flux influences the secondary coil, and because of that, since there is a influence of the primary coil, okay, in terms of flux, there will be a small amount of current flowing in the secondary coil, and that is what causes mutual inductance. Yes, and that is what is going to happen in a transformer. So the voltage across secondary coil, the voltage whatever you get here is now denoted by V2, which is going to be N2 by N1 into V1, okay, or the amount of current that can flow in the secondary coil is given by N1 by N2 into I1, where I1 is the current in the primary coil, N1 is the number of turns in the primary coil, and N2 is the number of turns in the secondary coil. Okay. By using this relation, we can build a linear variable differential transformer. Okay, what is this LVDT? LVDT is displacement sensor, which is based on the idea of a transformer. So I can convert a transformer to measure displacement. How is that possible? It is based on two related principles. The distance between two coils of a transformer is varied. So what happens? There is a primary coil, there is a secondary coil. Okay. So what happens is, okay, if I try to take a core and I wound the core with the primary coil and a secondary coil, now there are two coils. So what would happen is, if I apply a voltage to the primary coil, this will create some flux, and this flux will now influence secondary coil. There are possibilities that because of the flux this may start moving around, okay. Or the second possibility is the coupling coefficient between the two coils is varied by physically moving the core while the two coils are fixed. So what we now do is, these two coils are fixed. Because the two coils are fixed now, what we can now do is, the amount of voltage that we come across the secondary coil can be changed by changing the core. So I can keep changing the core. So when the core keeps changing, the voltage across secondary coil can be changed, and that is the principle on which LVDT is basically used as a displacement sensor. Okay, let us run this video and understand what is this LVDT sensor is. Let us see what is the what is LVDT by just going through the video. Okay, it is actually
LVDT is also known as linear variable differential transducer or transformer. It is a passive transducer which measures displacement. It consists of a primary coil wounded on a hollow cylindrical rod and is connected to the AC source. It also consists of two secondary coils having equal number of turns and is wounded on a hollow cylinder at equal distance on either side of the primary coil. The two secondary coils are connected with each other in series opposition, so that the net induced EMF of the two secondary coils becomes we see that a movable soft iron core is placed inside a hollow cylinder. Position of this core with respect to the two secondary coils will affect the magnetic coupling between the primary and two secondary coils. Let's now understand how this LVDT works. We see that when an AC source is activated, alternating current starts flowing through the coil, due to which varying magnetic field is produced. Now when this varying magnetic field interacts with the secondary coil, an EMF is induced in the two secondary coils. We see that initially the core is placed in such a position that equal EMF gets induced in both the coils, due to which the net EMF of the two secondary coils becomes 0. This position of the core is known as null position. Now if we move the core towards the right, we see that the flux linking with coil S2 becomes greater than the flux linking with coil S1. As a result, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Similarly, if we move the core towards the left, we see that the flux linking with coil S1 becomes greater than the flux linking with coil S2. As a result, EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net EMF shows a positive value. Thus, LVDT uses the magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position.
Okay. So very nice video to just understand what is the working principle of LVDT. Okay. So in an LVDT, what we find is there are one primary coil and two secondary coils. Okay. The two secondary coils are connected in opposition. So what happens, because you are connecting them in opposition, the voltage will be now series. The current that is flowing through them will become, they are now in series. So the current is now going to be in series. The output is 0 if coupling is balanced. Now, whenever you have primary coil, two secondary coils, so you are applying, you are applying voltage across the primary coil, then there is a core available there. If the core is at the mid position, the voltage that you come across secondary coil will be 0. But if the core moves towards right or the core moves towards left, okay, the coupling activity imbalances. So there will be more voltage available across ES1, that is the secondary coil, or there will be less amount of voltage available across second one. So by having this differential activity there, by having a differential activity, okay, you are able to measure the displacement of the core, and that is what is the working principle of LVDT. Okay. So this is the circuit diagram for LVDT. So you have a primary coil here, then the core here, then there are two secondary coils. Okay, the voltage is now taken across the secondary coil. So what happens is, whenever you apply voltage here, the core position decides what will be the voltage available across this. If the voltage here is positive, it implies the core is placed here. If the core is pulled out, okay, if the core is slowly moved out, the voltage here would become negative, indicating that okay, there is a displacement happening on the core. So the displacement is now converted to a voltage. Okay, and that is what the logic of LVDT is. Okay, so the advantage of having an LVDT is it detects both distance and direction of change. It's a very interesting thing. So suppose if I have an LVDT, suppose if I want to find out okay, whether it is moving, the displacement can be measured, plus whether it is going forward or it is going backward can also be detected because of LVDT. So you can measure the direction plus the amount of displacement. Okay, if the core is basically placed here and if the core is moving towards farther, you can now find out how much of displacement has occurred. Now you can also find out whether the core is actually going back or it is going front, and that is why we call it as linear variable differential transformer. Okay. There are multiple properties, so let us not discuss about all the properties. Let us quickly go to the next immediate activity, that is, typical voltages are up to 25 volts and it is usually below 5 volts. Resolutions can be very high, okay, around 10 to 20% of length of the coil. The last thing that we discussed today is the piezoelectric transducer. Okay, so let us understand what is this piezoelectric transducer is. So piezoelectric effect is the generation of electric charge in crystalline materials upon application of mechanical stress. So it's a very interesting thing that we need to understand here. Okay. Suppose if I take a transducer, assume that this is a transducer, okay, is a piezoelectric transducer. If I apply a mechanical stress, okay, there is an electric charge generated, and that is what is piezoelectric effect is. The opposite effect is also equally useful. Application of a charge across the crystal causes mechanical deformation in the material. Suppose, okay, I take a piezoelectric material here, okay. So what I do is, if I apply voltage, this material would get deformed. That is the reverse process. So you can basically have two important activities here. The two important activities are, one is, if I take a piezoelectric material, if I apply pressure, voltage get generated, or if I apply voltage, this will now start vibrating. Okay, that is how we can use a piezoelectric material. The piezoelectric effect occurs naturally in materials such as quartz, okay, or silicon dioxide. So it is a natural phenomenon of any material. It was first used in 1917 to detect and generate sound waves in water for the purpose of detecting submarines. So it's a very interesting thing. So during those days when World War was basically being done, the Germans were able to send submarines to attack the enemies. So to find out in what direction the submarines are coming, or whether the submarine is really coming in, they used to use this piezoelectric effect. So what they used to do is take silicon dioxide, a thick piece of silicon dioxide, they used to submerge in the water. So whenever you submerge it in the water, now what happens, they will be able to connect through wires. Okay. So whenever there is a pressure, okay, whenever submarines move around, they introduce lots of vibrations. These vibrations will go and hit, the water vibrations will go and hit the piezoelectric material, because the pressure is now going to change. The stress is going to be applied, there will be change in voltage. Now by changing the voltage, they can now find out whether submarines are available within the water. And that is how piezoelectric played a very important role in world wars. Now let us see how does this work. Okay. Now we have taken a silicon dioxide here. Okay, we have silicon dioxide. There are silicon materials plus oxide materials. Okay, deformation in one direction B displaces the molecular structure so that a net charge occurs as shown. So what happens? If you see here, it's a silicon dioxide molecule. Okay, the voltage across this is now going to be 0. Suppose you apply a pressure or you apply a stress. You apply a stress here. The top portion becomes plus, the bottom portion becomes minus. Similarly, you remove, you are trying to elongate, or you are trying to remove the, you are trying to elongate the material. So what happens? There will be a plus on the bottom, a minus on the top. So what happens? There is a charge that is being accumulated across the material of silicon dioxide because of deformation. If you compress it, you get a plus on the top, minus on the negative. You try to elongate it, you get a plus at the bottom and minus at the top. Similarly, if at all you apply a voltage, a plus voltage on the top, if I apply a plus voltage on top and negative on this, what happens? This compresses. Suppose if I reverse the potential, if I apply negative here, positive here, negative here, it elongates. So that is the effect of piezoelectric transducer, and it is governed by a polarization vector, which is given by P is equal to d sigma, where d is the piezoelectric constant and sigma is stress in the material. Okay, so this is the basic theory of piezoelectric effect. Let us see what is a piezoelectric devices. So we have taken a piezoelectric device which is having a thickness of d, and there are two electrodes on both the sides. Okay, we have a thickness d, and now it is like a capacitance. Now because this is an electrode, this is an electrode, and there is a dielectric here, it is now like a capacitance. Now let us see how does this work. Okay, assuming force is applied on the x-axis. So assume that this is the x-axis. Okay, this is your x-axis, and we apply force on the x-axis. When you apply the force on the x-axis, okay, now what happens? The charge is generated, and it is given by Q is equal to d into Fx. So what happens? Okay, whenever you apply a force on this piezoelectric device, okay, there is a charge that is going to be getting accumulated, and that charge is going to be given by Q is equal to d into Fx. Now we know that voltage across a capacitance is given by Q by C. Substituting for Q, we now have voltage is going to be given by d Fx d by C epsilon A. where C is given by epsilon A by D, where D is thickness and A is the area of cross section of the device. So what is happening, if at all you apply a force on the piezoelectric device, there is a voltage that is going to get generated, and that voltage is going to given by V is equal to D11 Fx D by epsilon A, and that is what is the basic working principle of a piezoelectric device. So we are now able to convert the change in the force to voltage. So whenever you apply force, this force deforms the material, and because there is a deformation happening on the material, what is happening now? Okay, because of deformation, the two electrodes are now coming closer. Because the electrodes are now coming to closer, they try to deform. Because there is a deformation happening, what is happening? D is going to change. Because D is going to change, you are able to change the voltage. Okay, and that is what is the basic working principle of a piezoelectric device. So we are now able to understand, okay, a simple microphone. What happens in a microphone now? These two are the electrodes which are basically being fixed, and you have put a piezoelectric crystal on this. So what happens when the acoustic wave falls on this material deforms. Okay, so because it's a piezoelectric ceramic, so what is happening? Because of the vibration, so when the vibration starts happening, the piezoelectric crystal deforms. Now this deformation would now lead to a change in impedance, and that change in impedance can be converted to voltage. So we are able to now convert acoustic pressure to voltage, and that is what a piezoelectric microphone is. Similarly, if you see, assume that you have a microphone, it's a piezoelectric microphone now. Okay, what happens in a piezoelectric microphone? You basically have a piezoelectric crystal there, or a piezoelectric device. Okay, and then you have some diaphragm sitting on it. So whenever the sound waves falls on it, this will now start vibrating. These vibrations will start deforming the piezoelectric crystal, and because of that, a voltage gets generated. Now you are able to convert sound to electrical signal. So whatever you are able to speak, you can capture it, convert it into a voltage which could be now transmitted through your communication medium. Similarly, okay, you have a piezoelectric buzzer. In a piezoelectric buzzer, what happens? You have, okay, you can take a piezoelectric crystal. Now you apply voltage across this. Because voltage is applied, a charge will be generated. Now this will start vibrating. This vibration will now automatically generate an acoustic signal, and we can now call them as buzzers. So we are able to now have actuators. So it is also called as piezoelectric actuator. So now let us now go back and discuss. There are two important concepts here. So here what is happening? You have two electrodes. These two electrodes and a dielectric here. It's a piezoelectric material here. They form a capacitance. This is an electrode. In between you have an dielectric, which is a piezoelectric dielectric, and all this put together forms a capacitance. Whenever you apply force, these electrodes deform. Because of electrodes going to deform, piezoelectric material also is going to get deformed because of force, and that is going to change the voltage, and that voltage is a measure of the force applied on the piezoelectric material. So you are able to measure the force, and that force is now directly related to voltage. Reverse is also possible. What is reverse now? Suppose you try to apply force, okay, you are able to get voltage. Now if you apply voltage, what will happen now? This will now start deforming, it will change, it will start oscillating, and that is what is an actuator now. So you are able to have both a sensor and an actuator based upon piezoelectric effect. Let us now conclude it. Yes. So we have discussed, okay, about sensors, we have discussed about actuators, and both of them are part of your transducers. So a sensor is an input device, an actuator is an output device. Both combined together, okay, or both of them are integral part of transducers. In a transducer, what happens is one form of energy is converted to another form. A sensor, for example, is a transducer which captures physical quantity, converts it into electrical signal. The electrical signal is again taken by an actuator, converts it back to physical quantity, and that is what is an actuators, and all of them together we call them as transducers. So there are few types of transducers which are called as RTDs, wherein it is called as resistive temperature detectors, or we also have thermistors, thermal resistors, linear variable differential transformers, or piezoelectric devices. all these 5 of them have been discussed, and we also understood some of the applications of what are the applications of transducers. Let me stop here and then conclude our discussions. Okay, so let us summarize. So what we discussed in these 4 to 5 classes are, okay, one is the communication part. So what we discussed in communication is the sensors which forms the front end. Okay, like it could be a piezoelectric, it could be a RTD, which captures the data coming from a microphone, and that data to be transmitted, you have to perform modulation. So we try to do modulation using amplitude modulation, frequency modulation, or phase modulation. Now, the signal that is being coming out from a microphone, okay, which is going to be electrical signal, is modulated using amplitude or frequency or phase, and then they are now launched onto a channel. So to launch it onto a channel, I can use an antenna. Antenna is an actuator, or antenna is a transducer. Signal now available on the channel is now captured by an antenna at the receiver side, which is again a transducer. The signal is now converting electromagnetic signal to electrical current. The electrical current is now being processed by your demodulator, and you extract the message from the channel, from the signal. That signal is now given to an actuator, which is basically a microphone or a speaker. The speaker will now convert the electric signal back to your physical quantity, that is your sound. And that is the entire system. Whatever we discussed now consists of what? The sensor, the modulator, the antenna at the transmitter, channel, then the antenna at the receiver, then a demodulator and an actuator. All this is what your syllabus is basically with respect to module 5. You have communication modules and transducers. So this is all what we discussed in this 5-day session, right? Let me stop here, and before I could conclude, let me tell you, communication is a very, very important part of electronics, and for communications to happen, you need to acquire data from real world, and this data acquisition is done with the help of transducers, either a sensor or actuator, and both of them together helps us in establishing communication from one point to the other point. So let us stop this discussions here. Okay, before I could wind up, see, more information on communication and transducers are available in the website. Please visit the website, you will be able to get more information there. Plus, I have also given my email ID, you can also communicate to me over email. Lastly, I recommend all the students to attempt Module 5 because it's a very interesting thing. If at all you are able to attempt this, you need to be thorough with amplitude modulation, you need to be thorough with frequency modulation, you need to be thorough with phase modulation, and also understand the working principles of all these transducers. So I wish you all a very good luck. I hope all of you would be able to attempt in your exam Module 5 question, okay, and you will be able to really write very good answers for all the question that has been asked. Lastly, which I wanted to mention is, if at all a question is asked, there are 4 ingredients that you have to really write for every question to get full marks. The first ingredient is the theoretical definitions. Second ingredient is you have to write a block diagram, which is very much mandatory. Third ingredient is you have to write a graph or a mathematical equation. The last ingredient is you may have to write an example. So if at all you are able to give 4 important components for every answer, you will definitely get full marks. The first is theoretical definition, block diagram, mathematical equation or a graph, and lastly an example. If at all you try to give an answer with all these 4 ingredients, definitely you will be able to get full marks. So I wish all of you a very good luck, and let us hope to meet next time next semester. Thank you very much.